Thank you for coming to my talk. This is a collaboration between the Met Office and the National CVS Storms Lab in the US. So as we've already heard quite a bit, that wind turbines are an important sort of renewable energy source, and that's not going anywhere. It's going to keep we're going to keep using more of it, and as a result, that's a growing threat to the weather radar data quality. Typical dualpol quality control approaches work quite well with ground clutter and other things, but wind turbines, unfortunately, we tend to struggle with those. There exist Doppler filters, which again are very good for stationary clutter, but again, these also often fail with wind turbines, and that's principally because of the moving blades. And so in this work, at first I will describe our previous work on switching on and off a Doppler filter for stationary ground clutter. And then in the later part of the talk, I will talk about the current work we're doing using spectral dual polarization parameters to detect and flag wind turbines dynamically. So a quick refresher, with weather radars, you really want to have the lowest elevation data that you can possibly measure. And this exaggerated cartoon here, you can see that the lowest elevation data is contaminated with clutter in both cases. Close to the radar, the higher elevation data is still representative, so we could still use that. Further away from the radar, you really want to know if you can use the lowest elevation data, you want to use it, and if it's not usable, then you've already lost a lot of the data. So a quick refresher about Doppler filtering. The idea is that you can take your signal from the time domain into the frequency domain. And if you have stationary ground clutter, you expect most of the power for that to be at the zero velocity component. And you can have a notch filter where you cut out that power at zero velocity. And you can have some more advanced filters such as CleanAP, which was developed by the NSSL group, where you can reconstruct the original signal and then you can obtain the original data for the rainfall. Unfortunately, you don't want your Doppler filter to be turned on all the time, because you have this thing called the zero isotop problem, where if you have weather moving perpendicular to the line of sight to the radar, it will have zero radial velocity, and therefore you might erroneously delete that data if you're just deleting anything that's not moving towards you or away from you. And another thing to highlight is that CleanAP is able to adjust the width of the notch dynamically, so that's an interesting point. And now we'll talk about that work about switching it on and off. So we developed a neural network, actually two of them, but you can think of them as just one black box, and it is meant to classify into three outputs. So for a given pixel in the data, one gate, it will tell you if you should use the unfiltered data. And that means it believes that it's pure rainfall signal, there's no contamination, so we can just use that. If it believes that there is contamination and that filtering that contaminated data has worked, that is, the filtered data is now good enough to use, it will then classify it as filtered. And if it believes that there has been contamination, but filtering hasn't helped enough, then it will tell you to censor, so that we go back to the procedure of using a higher elevation data. So this the top part of this, which is one of the contributions we had in our paper, is very similar to what Federico just mentioned earlier, where you take IQ data for pure rainfall signal where you know there is no clutter, and we take clutter tiles, so we call them tiles because it's little cutouts where you get the horizontal, azimuthal and radial spread, so you can have the spatial variability. We can also have multiple elevations of this data, so we can test what feedback it makes to make for the trade-off between giving up on the lower elevation but relying on the higher elevation, where there's going to be a larger error when you do the vertical profile correction. Anyway, you can add the pure rainfall data, pure clutter tiles together, and you get the contaminated tile. And of course, you still have the original rainfall data, so you can use that as a ground truth, which is very useful. So We trained those neural networks, the two of them I mentioned, they have 3 degrees of azimuth, so 3 pixels there, and then 3 pixels in range. And there are 30 fields for each of these 9 pixels. And those 30 fields are down there. You don't really need to worry about the details, but generally it's about using the uncalibrated absolute autocorrelations for lag 0 and lag 1, both in H and V, and then the unfiltered and filtered versions. An estimate of the notch width by CleanAP, the values of ρHV for unfiltered and filtered, and then you have for angles like phi dp, or the angles for the lag 1 autocorrelations. We use sine and cos to feed them into the neural network, and the reason is because it wraps around at 2 pi or plus or minus pi depending, and you really don't want that to cause a problem in the input. So it's nice to have sine and cos, which don't have this wrapping around problem. And we also used circular variants of the autocorrelations. I should note that this is so because this is a small spatial window of 3 by 3 azimuth and gates, we used a fully connected network. I don't know what happened with the dashes there. I think cosmic ray in my presentation. So if we looked at the accumulations as over 6 days, you can see that on the left we have the existing scheme, which does not use a Doppler filter, and on the right we have the new scheme that was being proposed. And sensor data on the lowest elevation has been backfilled from the higher elevation, so infilling has been used. And you can see those bright spots everywhere. These would be the ground clutter contamination that was remaining in the data. And with a new scheme, so not only are we using more lower elevation data, but we have completely removed a lot of these bright spots, which suggests that we're getting rid of more of the clutter residuals. And the background rainfall rate has not changed, so that means we're not deleting any more rain. So that's good. And we did do some comparisons with rain gauges. Normally, you wouldn't expect a gauge to be in a cluttered environment, so they're usually in big open fields. But we did see some improvements already, so that's all good. Now on to the present work, wind turbines. So this is a scan at Thurnham radar, which is on the southeast coast. And these bright blobs in the sea there, these are all wind turbine locations. So you can see they've been flagged in yellow here. And the flagging here is done with a fixed mask. So we know where all those wind turbines are, and we just throw away that data at the lowest elevation, sometimes even the first or the second elevation scans. And this is a sort of last ditch approach that we have to do because there's nothing else that can help yet. But there are severe problems with this, because you can see this one here where we flag it all the time. It's not there right now, but it is there when there is anomalous propagation. So if you want to effectively delete everything that's there when it's there, you have to do it all the time, and then you're throwing away, in this case, perfectly good data. There's rain there. We should have kept that, but we're not, because we got the fixed mask. So I mentioned Doppler filtering doesn't always work with wind turbines, and the reason is something like this. This is again a cartoon sort of description, but effectively, instead of just the zero velocity power that you get from stationary ground clutter, in this case there are multimodal non-zero velocity components, so it's very difficult to detect them in this way. So I've taken this plot from a paper by Moasev and Chandrasekhar. It's called spectral dual polarimetric variables. So the idea is that instead of using the gate averaged values of the dual polarimetric variables, and similar to what somebody just said about the spectral noise flow, so this one is calculating the dual polarization parameters in the spectral domain. So you've got, instead of just one value for each pixel, you've got as many measurements as you have in your original number of pulses. And you can see there's the zero velocity signal there, which is going to be ground clutter, and you can see there's rainfall over there, so at higher velocities. And there, all I need really from this is that there exist those specific spatial characteristics that you can see with your eyes, and if you can see it with your eyes, I can teach a machine to do it. In practice, we're using something called the bootstrap dual polarimetric spectral density estimator. which was developed by the NSSL team. And the idea is that instead of just calculating the dualpolarimetric spectral parameters with your one set of measurements, you do some work to obtain multiple iterations from the same data. So you're bootstrapping and obtaining a more stable estimate. Because remember, this is a with the gate average values, you have all those values being averaged to one gate, and that gives you quite a smooth, stable value. Here, if you're using the spectral version, you have a lot of numbers, and there's a much higher, the noise on it is much higher, so it's much more variable. We use two sets of inputs. We use the spectral dualpolarimetric inputs I just described. So three rays worth, 3 degrees worth of, say, 35 pulses, 7 gates in range. And the 4 fields that we're using, and then it would be the ZDR and ρHV, but the phi dp I've split it up into cos and sine once again, because it makes it easier for a neural network to handle. And we use the power inputs then, so these are the gate average values for the unfiltered and filtered H and V channels, scaled by the noise floor estimates. So, and this is a rain tile, so these are one of the synthetic tiles I mentioned. And in this case, the rain power, so this would be uncalibrated power, lag 0. So the rain is 67, the ground truth is 67 dB, and the contamination is not much higher, and the filtered is not much higher. It's the same value. In this case, we would hope that the network will classify this as unfiltered. It would say just use that data. There's nothing wrong with it. And you can see there's the other parameters down there, the spectral dualpol I mentioned. In this case, the rain signal was 45 dB and the unfiltered, so the contaminated version is 66, and the filtered version is back to 45.4. So what we're saying here is that for the central gate, the filtering has worked, the notch filter has worked, it has done its job, and therefore the filtered data should be used. The unfiltered data is contaminated, we're not using it, we'll use the filtered data. In this case, the unfiltered version, the contaminated, is 81. The original was 49.9. And the filtering hasn't helped that much. It has worked a bit, but it's not enough. So we don't want to use this data. So we're going to label it as give up wind turbine clutter for this one, wind turbine for this one. Sorry, I accidentally clicked and it moved. Yeah, so that's the idea anyway. And using, therefore, we have these two columns, because I mentioned there's two types of data. There's the spectral dualpol and the power estimates. So the power goes down this column and the spectral dualpol goes down this column, and they get combined at the bottom, and an output is made, a decision is made for using the unfiltered data or the filtered data, or give up these two, clutter and wind turbine. The reason I've split them out is because I want to know where those wind turbines are, because I would like to go and verify if I can. And it's a very bog standard convolution neural network. It's looking for interesting shapes in the data, really, and it's just doing image recognition. And then it goes through several layers of pooling, which sort of forces it to get more and more abstract shapes. And then it goes through a fully connected layer, and then you get the classification come out of it. If anybody else is doing AI or machine learning stuff, I highly recommend looking at guild.ai and TensorBoard, because I use them to monitor the progress and compare different runs when I've changed different variables, different parameters. So we trained them for a total number of 150 epochs. One epoch is basically you show it all the tiles, all the training tiles. That's the end of one epoch. You update the weights as you go along. And then the next step is validation. At the end of one epoch, you run through the validation tiles, and you do not update the parameters anymore. You just want to see if the training has helped, if it's making a better output for out of training set data. At the end of multiple trainings, so after the 151, we pick the best, the one with the highest validation accuracy. And then we have a third data set, the test data set, where in this case, on the horizontal there, there's unfiltered, filtered, clutter, and wind turbine for the ground truth, because that's where we have the original data. And then on the vertical, we have the neural network, same parameters. The diagonal elements will then represent correct detection, so unfiltered or filtered has been correctly labeled. The off diagonal then represent the false positives and the false negatives. And we can see that these numbers are quite low, so it's about 2% at most. of the data set. So it's doing quite well. The overall accuracy for each class is shown down here. Oops, 95%, 84%, 86, and 92. So these don't look amazing, but it actually works quite well on real data. So this is a dry case, clear sky at Hamilton Hill. You can see everything that would normally be noise. It says use the unfiltered data because we don't care. There's nothing interesting there. It doesn't do any filtering because there's no rain on there. There's no improvement to be had. Clutter, all the red blobs it's correctly labeled as clutter. Wind turbines are over here where we know they are. So that's very good and very pleasing that it's detected them. There are quite a few of these false positives here and there, but they tend to show on and off, so they're not constant, which is helpful. A rainy case, this is a gloriously messy example. So the wind turbines are still around here. There-ish, I couldn't even point them out properly. But the great thing is that it has detected in some cases, decided, okay, these are still wind turbine tasks. I don't want to use them, so flag them as black there. A lot of the data has decided actually we could use this if we filter it. So it has decided to filter. Even on the area where there's usually a lot of ground clutter, it has decided to filter those. And then some of it is said, like down here, there's no rain on there, so let's just throw that away. It's clutter. So those were single scans. And now this is an average over a 3-hour period. Because that's how you often see, you would see if there are very faint signals, for example, these add up. Now, on the right here, I have used the fixed maps that I mentioned before, the fixed clutter map. So you can see it's notched out a large area. And this is the average reflectivity with nothing done to it, just the raw data. And you can see that the actual wind turbines clutter is actually smaller than this area over here. The new scheme has correctly decided not to throw away any more data than it has to. And you can see over here, really close to where this one would have deleted, there isn't any extra bright spots. So you would expect it to be bright if there were clutter breakthrough, if there were residual signals over this 3-hour period, but it's not there. So we're quite happy that we're now recovering a lot of the data. We're not throwing away any more data than we have to. And this is a diff between the average reflectivity at the top and the filtered version at the bottom. So we're seeing that over here, there's no loss in the original rainfall. So the rain signal is the same. Yeah, so in conclusion, I've just shown that this wind turbine situation is not going to get better for us with weather radars. The dual polarization spectral parameters are very helpful for detecting them. And this TAS approach and the synthetic TAS thing has worked really well for us as well as for Federico over there. And yeah, we're planning to improve the model a little bit if we can. And currently we need to do some optimization because the runtime is about 2 minutes per scan, but that's there's a lot of space for optimization there. So we're quite optimistic about that. Do you have any questions?
When you say 2 minutes per scan, you mean per sweep?
So it's just the runtime on the computer that is doing the processing. So currently you can't run this in real time because the scan is about 40 seconds. We do need to bring it down to about 40 seconds or under 40 seconds instead of 2 minutes. But that's only because the code I wrote, I wasn't trying to make it fast. I was trying to make it correct. And then the next step is going to try and make it fast.
Simple question. So, if you go to another site, is there something then the procedure is the same? So you have to individually do that for every site, or
no, so
just do that once, or?
Yeah, that's right. So what we found with the paper that we published before with just the clutter filtering, we found that this technique of matching rain and clutter tiles works really well. That once you've trained it on one site, it works on all the other sites. But we're also very lucky that all our radars are built to the same spec. So there's very minor variations between them. So we've not seen any need to retrain at any point. But in practice, if you had 2 or 3 different types of radars, you could easily add those to the training and use the same neural network. So you don't need to do it separately.